we have to study the organization of a basic computer. So to understand, to uh, deeply grasp the concept of an organization of a basic computer, we will move step by step. Let us first see a few definitions, so which we will see in the future, near future. One of the definitions is instruction code. What is an instruction code? An instruction code, it is a group of bits that instruct the computer to do a certain task. So these bits tell the processor, the computer, what it has to do. So these bits are called as an instruction code. Usually the instruction code is divided into parts, and one of the most important part is the opcode or the operation code. And what is that operation code? This operation code is a set of bits which defines the operations, the particular operation that has to be performed. Like, has the computer to perform add, it has to perform subtraction, what it has to do exactly. So it will give the exact code. A code will be there that will specify which operation the computer has to perform. There is a simple concept, a basic concept, that is called stored program organization. That is, if we make a very very simple computer, what will be its organization like? So if we the simplest way to organize a computer is to have one processor register. So there will be one processor register and instruction code, which usually will have two parts. One part will be the opcode thing and the other will be an address part. So the simplest way to organize a computer is something like this, that I will have a memory in the computer. Fine, this is the memory, and this memory will contain may have two separate segments, one segment for the instructions, fine, and the other for the operands. And there will be inside the processor there will be a register that is called the processor register, that is also called accumulator, denoted by AC, and the operations will be done here. Operations are to be done on the things, on the data that is here, right? This is the operand which is in the memory, and what operation we have to perform is here, the instruction, it is also in the memory. And let us say for an example that the memory is of size 4096 into 16. 4096 into 16. It means one word of memory is 16 bits, and the total number of rows, total number of words in this memory is 4096. And there will be an instruction format. So the instruction here, that is of 16 bits, will have a format. It will be something like this. There will be an opcode and there will be an address. So this one word of this instruction is here. It will be of two parts: opcode, that is operation code, and address. What will be the size of this address? This address is address of the memory. Since the memory is of size 4096, fine. So 4096 obviously means 12 bits. 2s power 12 is 4096. So to address this memory, we need 12 bits. That obviously means 0 to 11, that is 12 bits will be address, fine. And this whole will be 16 bits because this one word is 16 bits. So it will be 0 to 15, that is his whole thing is 16 bits. And since this is 12 and the remaining will be 4 bits, that becomes the opcode here, fine, 12 to 15. And this operand obviously will also be 16 bits, it will be 0 to 15. So a simple computer will have at least these things to operate upon. This instruction format will tell what to do, the thing on what address the data is given here, And where to do it, the operation will be done with the contents of the accumulator. So operand may come from here and maybe added, subtracted or something with the contents of accumulator. So this will be the simplest thing. There are no other registers here, just the simple this register and done. And since we just saw that this 16-bit address consists of opcode and address, but we must remember that this address may be of two types. It may be a direct address or an indirect address. The address which we just saw here, this address may be of two types. It may be a direct address or an indirect address. A direct address means that when we go to that address in memory, we will find the operand. Indirect address means that if we go to this place in memory, there we will find the address of the operand. And so this is an indirect address. But now a question arises, how will the computer know whether this address is a direct address or an indirect address? For that, obviously, we need a bit here. So that is what is shown in this diagram. So usually it will have this format. So there will be an address and this most significant bit, in this case, which is the 15th bit, this I bit, this will tell us whether this address is a direct address or an indirect address. So if this I bit is 0, the address is a direct address. If this I bit is 1, the address is an indirect address. And the opcode remains there. And if we take the same example that this is 16 bit, this is 12 bits, this is 1 bit, so opcode obviously will be 3 bits long. Fine, 3 bits. What is opcode? It is the code which tells the computer what to do, whether it has to do addition, subtraction, shift, what it has to do. This is the code for that thing. Fine, everything will have a code. For example, 000, it may mean and. 001, it may mean add. It depends on the organization of the computer. What does that code mean? And we can clearly see that in this computer there are 3 bits for opcode: 12, 13 and 14. So 3 bits will have 8 combinations. That means that this computer can perform at most 8 operations. Because there are only 3 bits in the opcode, at most it can perform 3 operations on the contents of memory, 8 operations on the contents of memory. The operations may be and, add and other operations like that. And here you can see this thing, this B and C. This B denotes here what a direct address means. So for example, this is the instruction in memory. Instruction, fine. It will have 3 parts: the I bit, the opcode and the address. And since this is 0, it means that this is the address of operand. So we will go to 457 location in this memory. There we will find the operand. Fine. And we will take this operand. Since here it is written add, it will be obviously in binary. For simplification, it is here like this. So if this is add, so the operand will be added to the contents of accumulator. Fine. And the answer will be stored into accumulator. And if this is 1, it implies that this address is an indirect address. That means we will go to this location here, 300. Whatever is written here is not the operand. This is the address of the operand. So we have to go to 1350. Then we will find the operand and then we can perform this required operation. So this diagram is showing the difference between direct address and an indirect address. Now let us have a look at the registers of a basic computer. So in a basic computer, there will be at least 8 registers, these 8 registers. And we can see, we can have a look at them. One is the data register, fine, and it is denoted by DR, data register, and it holds the operand. So whenever an operand comes from memory, it is put in data register. So it is related to operand, the thing on which we have to work, the operand. And if we take the same example where a memory has a size of 4096 into 16, fine. If we suppose that we have a computer, basic computer with this memory, this obviously means 12 bits of data and 16 bits in a word. So since a word is 16 bits, that means operand will also be 16 bits. That is why here we are showing 16 bits in the DR. The data register will be of 16 bits, fine. And next is AR, which is called the address register. It holds the address of memory. So for example, I want to go to certain address of memory and bring instruction from there or bring operand from there. So that address will be held by the address register, AR, fine. Sometimes it is also called MAR, memory address register. And this obviously will be 12 bits because the address here is 12. There will be another register called AC or accumulator, which is also called a processor register. It obviously will be 16 bits because one word is 16. There will be another register called IR, which will hold the instruction. Fine, it will hold the instruction called instruction register. It again will be 16 bits because word size is 16. Another register will be there called PC, which is called a program counter. And program counter holds the address of instruction, and it is actually holding the address of a next instruction which we have to execute. So since this is an address, it again will be 12 bits. There will be another TR, temporary register, for holding temporary data during the execution of instruction. Maybe for example, we are adding some numbers and we have a temporary data that can be stored in a temporary register, obviously 16 bits. And we also have input and output registers inside the processor. So these input and output registers take or give data to input and output uh, devices, which obviously will be in character form. So input register will take one character and output register will output one character, fine, at a time. So character we know is 8 bits, that is why this will be 8 bits. So these are the 8 registers of a basic computer. In a modern computer, we have a very large number of registers. Some have 32, some have 64, but these are the basic set which we require to build, to organize a basic computer. And how these registers are connected can be seen in this diagram. So these are the 8 registers which are mentioned here. This 1, 2, 3, 4, 5, 6, 7, and 8 registers. And since they all reside inside the processor, and we do not want separate buses for each register, which obviously will be uneconomical. And we know that we for this thing we use a common bus system, fine. So now this diagram is showing how these registers will be connected to a common bus. And what is a common bus? It is a bus that is common to all the registers, and all the registers use this bus, but obviously one at a time. And we know that this bus can be made up of can be made in two ways. whether it can be made using multiplexers, or it may also be um, made using 3-state buffers. So there are 2 ways to make this bus. And for example, if it is made up of multiplexers, there will be some selection lines that will control uh, which of the registers can use this bus. Fine. So for example, there are 3 selection lines here, because there are 8 registers. 8 registers need 3 selection lines. So for example, if this selection line is 111, 111 means 7. So here we can see that 7 is implying to this thing. So this memory can use this bus, others cannot use. If this is 001, 001 means 1, that means address register can use this bus, others cannot use. In the same way, if this is 010 implying 2, that means PC register can use this bus, others cannot use. This way, simple uh, multiplexer can be used to make this a common bus. Now we can see here that this every register is connected to this bus except INPR, and this is an input register. It obviously will take its value from some other place, maybe from keyboard it will take a alphabet. So it is not putting something, it will not be there will be no output to the common bus and no input from the common bus. To an output register, there may be something written on to the output register, but the output register will not give its value to the common bus. It will give its value to some other device, for example the monitor. And uh, this memory will also be connected to the same bus. Fine. And we can see here that many registers here will have a clear line here. Fine. So clear means when we want to clear the contents of it, put all values to 0. Fine. So this is a control signal generated by the control unit. Whenever we want to clear something, we want to clear the accumulator, so this will do the needful. In the same way, if we want to increment some register, we want to increment the contents of accumulator by 1, there is another control line. For data register, again, for PC also there is an increment if we want to go to next instruction. And AR also we have an increment here. Fine. And AR, PC, DR, AC, IR, TR, and output register all will have a load signal here. This is load control signal, LD. Load obviously means that take the value from here and store it on this register. So load. So whenever this load is on, the register will take the value from the bus and will store it. If this is off, the register will not take this value. This is load signal. Okay, now we can also see in this diagram that a clock pulse is going to all registers. Okay, and additionally we can also see here, this is the circuit, the ALU thing, arithmetic logic shift thing, which is doing its operation here. And we can see accumulator is connected, the output of accumulator goes to bus as well as to this thing, because we know that whenever we have to, for example, add 2 numbers, one number will come from DR. Fine. The second number will come from AC. So this is the way the computer does its work. So if I have to add 2 numbers, one number will come from DR like this, the second number will come from AC, and they will be added and the answer will be stored in AC. Or it may happen that something may come from keyboard, that will go to adder or shifter. Fine. Then it will go to AC, and it will be like this. That is why it has three ways to get the data here. and when we add something, it may produce a carry, so that will go to here, this bit. Fine. Okay, now let us say, for example, I have to get this something from here onto the bus. Fine. So some I have to get some instruction, for example, from this memory, and that instruction should go through the bus, and it should go into the instruction register, that is IR. So what should I do? Very simple. Since I have to take value from here, so I need to enable this line. So to enable this 7, we should put 111 here. So it should be 111. That means the contents of this will go onto the bus. And since this is a large memory, which word should go here, that is decided by this address. So address register will tell which word. For example, address register says the first word, 0th word. So the first word will go here. And what it has to do, whether read or write, that will also decided by control line. So if it is read, the value from here will go onto this bus, right? And this value will be input to all registers, but only that register will accept the value which has a load on. So since this thing is to be accepted by the instruction register, so this load will be on. Obviously this will again be decided by the control unit, and values will, the instruction will be loaded onto this register. Fine. And this way all other registers will work. Fine. So if I have to take an operand, for example, I have to take an operand to DR. Again, address will be put here, read will be put here, 7 will be selected, and the operand will go onto this bus. And this operand obviously should go to the data register. That means this load should be on, and the operand will be taken into DR. Fine. So this way, this whole thing will work.